All right, the last video I want to talk about in the series of how to solve partial differential equation is something called semi-infinite domain. So semi-infinite domain. And semi-infinite domain, as I would think of it, is sort of a variation of the heat equation. It's kind of close, but not quite. But the basic concept is that instead of analyzing the temperature on a 1D rod, now we're analyzing the temperature on a 2D plane. So let me just draw a brief diagram right here. So this is your x-axis, this is your y-axis, and then you have a plane that looks like this. And then so 0 on the left, on the right end is A, and on the top end is B. So this is just some constant values. So the basic equation for the semi-infinite domain is as follows. So let me actually so it looks like this. U of x plus u y equals to 0. So the two fundamental variables are x and y instead of x and t. So we're just gonna do our separation of variable thing, and that is turn them into the form of like this: x double prime of y plus x y double prime equals 0. And then we just tweak this expression a little bit. We get x double prime over x plus equals to negative y double prime of y equals to negative lambda. And then the domain of x is 0 smaller equals to x, smaller than equal to a. For domain for y is 0 to smaller than y, and then smaller than b. But as you can see, as you might have told that the boundary condition for this one has a lot of them. So one, you can have a boundary condition right here, one have boundary condition right here, one boundary condition right here, boundary condition right here. You can vary 4 of them, and then you can make them 0 temperature insulated. Sometimes you can make them bounded, temperature bounded, or unbounded. But so we're just gonna say boundary condition varies depending on situation. So boundary condition varies depending on situation. So but again, but that doesn't stop us from doing what we have been doing, and that is solving these two differential equations. Oh, by the way, lambda greater than 0. So, all right, let's go ahead and solve these two. So what we get is x double prime plus lambda x equals to 0. That will give us so x double prime of x equals to negative lambda. That will give us x double prime plus lambda x equals to 0. R squared plus lambda equals to 0. R equals to plus or negative square root of lambda I. So this is like we have done a million times, so I'm not gonna discuss too much about it. X equals to C1 cosine square root of lambda x plus C2 sine square root of lambda x. Differentiate x prime equals to negative square root of lambda C1 sine square root of lambda x plus square root of lambda C2 cosine square root of lambda x. Okay, and then again, what we do here is apply boundary condition, find lambda and xn. So we're done here, and then we're going over here. So the y part is a little bit different compared to the one you see in the wave equation and the heat equation. So what you would end up, because there's a one more negative sign in this partial differential equation, what we will get is, let's write that down first. A negative y double prime over y equals negative lambda. What you end up is y double prime negative minus lambda y equals 0. So r squared minus lambda equals to 0. That will give us r equals to positive or negative lambda. So and then your y term will become something like this: y equals to c3e square root of lambda y plus c4 e to the negative lambda square root of lambda y. And then we differentiate just as we did in the x term, equals to square root of lambda c3e square root of lambda y minus square root of lambda c4 e to the negative square root of lambda y. And then we do the same thing because we have 4 boundary conditions right now. So we should have, two boundary conditions for the y, one on the bottom and one on the top. So one on the bottom, one on the top. So again, so just apply BC, find the yn. So all right, so this is where it gets interesting. In the semi-infinite domain, oftentimes that our temperature, U needs to be bounded because, think of it as a slab of material that maybe get heated on this side or maybe heated on that side, and then you have an infinite long of material going up or going to the other side. So that means as the length of the plane approaches to infinity, the temperature has to equal to 0, and because of that, this exponential growth term is if we have this exponential growth term exist, we won't be able to meet that requirement, and that is temperature equals to 0 as we approach to infinity. So since U needs to be bounded, so that means limit of b approach to infinity, U equals to 0. So this means y. So in this case, we are extending our y upward to infinity. You can make x extend to infinity, but you can just do you can just switch the signs a little bit, and that's you can get a different type of solutions. But we are focusing on this specific case, and that is the one that you will mostly encounter on exams. So y cannot have exponential growth or positive exponential term. So positive exponential term. All right. So now so that means this term, this C3 term will always be canceled out, no matter, in many cases, as long as the this b is going to infinity, this exponential term in y will always get canceled out, because that just won't meet our conditions. So formulate formulate our final solutions, so u of x and y. That will give us 1 1/2 a0 plus infinite series of n equals to 1 a n x n and y n. So this looks like a Fourier cosine series, or u of xt xy equals to infinite series of bn xn and yn. So this is more of a Fourier cosine series. So it's very, very kind of vague, because you really have to, the way you approach these problems really depends on your situations, how the boundaries are defined, and etc. But I do want to go through two specific cases with you, so that you have a deeper understanding, or use this as a basis to tackle whatever problem you're trying to do, and tweak the numbers. Hopefully you will find a solution that fits your situation. So let's just do it. Let's go ahead and do it. So the first case is semi-infinite domain with 0 temperature ends. So infinite domain with 0 temperature ends. So let's draw a topic box again. And oops, that's not good. Let's draw that again. Okay. And I draw another box right there. Okay, good. So I'm gonna copy this diagram because that will be very useful. I'm gonna paste it right here. In our case, in this type of question, we're going to focus on the boundary condition as follows. So the differential equation is the same, and but our boundary condition is u at 0 y equals to 0, u a of y, so no longer L, this is a, equals to 0, and then u at x 0 equals to fx, and then limit as b approaches to infinity, u of xy equals to 0. So what the swing on the diagram is, so on this line, on the x-axis, this will be our initial heat profile, fx. And then these two boundary conditions that we are given here, that just tells us that on this boundary and on this boundary, the temperature is 0. So u equals to 0, u equals to 0 all the time. And the last boundary condition it tells us is that this boundary condition tells us that limit of as b approaches to infinity, u equals to 0. So this is the boundary condition that we're given. Okay. Actually, let me move this down just a touch. So just for better organization. Okay. All right. Then, again, because of our initial condition, the first initial condition, similar to what we did in heat or wave equation, x0 will be equal to 0. So that tells us that C1 equals to 0. Again, this will not be 0, so this has to be 0. So and then x of A equals to 0. That tells us actually, let me go ahead and write the x. So x equals to C2 sine square root of lambda x. So our second boundary condition is x of A equals to 0. That tells us that sine square root of lambda x equals to 0. C2 cannot be 0. So not x, this is A. Square root of lambda A equals to n pi, because in order to have to make the sine term become 0, lambda A square root of lambda times A has to equal to n pi. So the value of square root of lambda will be n pi over A, and the lambda will just equal to n square pi square over A square. So there you have it. And then let's turn our attention to the y term, because so based on what we learned before, that solving this partial differential equation will give us r equals to positive or negative square root of lambda, y equals to C3e square root of lambda y plus C4 e square root of lambda y. So because u is bounded, therefore y equals to C4 e negative square root of lambda y. So this term gets cancelled out. And there comes our final solution. U of xy equals to the infinite series of bn, xn, and the yn, and that's equal to infinite series of n equals to 1, bn sine square root of m pi over A. That's our value of the square root of lambda x, and then e to the negative m pi over A y. So we're just putting all the pieces together. And the last boundary condition, and that's the last boundary condition is not the boundary condition that we have not used yet. Actually, let me just add that really quickly right here. So we'll use bounded. That just means limit of b approach to infinity, u equals to 0. So that's it. That's just something I'd like to add on for your understanding. Okay, let's focus on attention to the last boundary condition. so u x 0, so that would equals to infinite series of n equals to 1 bn sine m pi a x, and then again, because y equals to 0, the exponential term reduces to just 1, so that equals to our fx in our boundary condition. So what you need to do is, again, solve for bn and n, and you're good to go. So this is one case for the semi-infinite domain, and then the second case is that, and this is our final topic. So actually I don't think we have enough space in here, so we're just gonna move down. So actually I'm just gonna copy that and paste it. Copy the entire thing and paste it. So, and then with insulated ends. And so, let me just write down my boundary conditions, and then I'll tell you what they mean. U x 0 y equals to 0. U x a y equals to 0. And now boundary condition, u of x 0 equals to fx, so initial heat profile, and limit as b approach to infinity, u x y equals to 0. So the only thing that's changed compared to the 0 temperature ends is these two boundary condition is different. Okay, so and what this difference interprets into our diagram is that instead of u equals to 0 on these two ends, we have u x equals to 0 on both ends. So that means heat will not be able to penetrate or will not be able to travel through these two boundaries. It will always stops right here. So that means they're insulated. All right. So similar to what we did in the heat equation with insulated ends. So when we differentiate, when we apply our first boundary condition, x prime equals to f x prime of 0 equals to 0, that will give us c2 equals to 0, because again, if you look at right here, that this gets 0, this becomes 1, so c2 has to equal 0 in order to meet the boundary condition. So x equals to c1 cosine square root of lambda x. We differentiate that again. X prime equals to negative square root of lambda c1 sine square root of lambda x. And then we apply the second boundary condition. X of a equals to 0. That tells us that sine of square root of lambda a equals to 0, and that will give us square root of lambda a equals to m pi, and the square root of lambda will equals to m pi over a, and lambda will equals to n square pi square over a square. So because and then we turn our attention to our solving the y. So let's go ahead and do that. So y double prime minus lambda y equals to 0. That give us r equals to positive or negative square root lambda. It's just, it's always the same. Y equals to C3e square root lambda y equals to plus C4e to the negative square root of lambda y. And then again, because u is bounded, limit of b to the infinity, u equals to 0. So that tells us y equals to C4 e to the negative square root of lambda y. And so yeah, let's just cross that out for better visual clarity. So this will give us, therefore, u of xy equals to square root of lambda n equals to 1, bn xn yn, and that will translate into infinite series of n equals to 1 bn cosine of m pi ax times e to the negative m pi over a y. Again, last boundary condition. So u equals to u of pi, so u of x and 0 equals to infinite series of n equals to 1 bn cosine m pi ax times 1 equals to initial heat profile of fx, and then we just again, we did this over and over again. Solve for bn and n. Okay, if you are able to watch all the way to the end, congratulations. This is everything that you need to know about semi-infinite domain. I choose not to cover the chapter 10.1 for the Sturm-Liouville equation, but because I think the concepts that we discussed in our topic of semi-infinite domain is very similar to what you would see in the Sturm-Liouville equations. And again, so I hope that at the end of the video, you should have a very clear idea about how to approach solving partial differential equations in general. You see, we always start with interpreting what our differential equation means, and then we use the method of separation of variables. We'll do some arrangements, and then we just go ahead and solve these simple ordinary differential equations, and then we just combine our solutions together. There will always be a boundary condition that needs to be left to be used at the end, so that we can solidify our final solution. But yeah, this is literally everything you need to know. We've come all the way from reviewing heat equation, wave equation, and then semi-infinite domain. So I hope my video helps for you to tackle the problem that you see in your exams, in your practices, in your homework. But other than that, thank you very much for watching, and have a wonderful day.